And I've put up my model solution. Well, slightly scruffy model solution, but there we go. I've had a number of questions about how you design that thing on, and I'm using the word design quite carefully, in fact, that thing on the right of the double inequality. And it's kind of up to you. You can do whatever you want there. It's just that whatever you put there has to fit those three requirements. So it's not like there's only one way of doing that. There'll be a couple of, well, in that particular example, there's sort of two things I can think of offhand straight away without having to think hard that I could do. But there's probably some others as well. So it's not that there's only one thing that you can do. So you designing that thing, when you're engineers all about design, isn't it? There's a little bit of design in maths as well. You've got to design that thing on the right in order to fit those three requirements. But what it is, it doesn't have to be just one thing. It just has to fit those three requirements. And in a sense, that's what makes squeeze theorem hard, because it has that level of creativity where you kind of have to make something up that works rather than following a set of rules. Question? Yeah, so what I did was I made the numerator bigger, but I could have made the denominator smaller. I could have removed the y squared from the denominator. That would unarguably have made the denominator smaller, and hence it made the rational expression bigger, and then I could have cancelled the x squared at the bottom and top. So those are the two things that are just off the top of my head I can see. Be very, very careful. So here is something that's not present in this particular example, but will be in others that you do. So I'll just give you a warning note now. Be very, very careful of playing with the powers of the variables. You would think that if you have an x squared and you change it to an x cubed, you've made it bigger. But you actually haven't, because x is tending to 0. And little numbers, if you put them to a power, they actually get smaller. So think of a half. A half squared is a quarter, but a half cubed is an eighth. It's smaller. So be very careful. As I say, it's not present in this example, but it is in others. Sometimes it's very tempting to change an x squared into an x cubed and say, oh, I've made it bigger now and everything works out nicely. But in fact, you haven't made it bigger, you've made it smaller. So just be careful of powers. When your numbers are small, powers do an opposite thing of what your instinct tells you that they're going to do. So just a little word of caution there. Okay, alrighty then. So that was yesterday's notes. Today's notes. Okay. Now, again, a couple of people, I don't think in lectures, I think it's in the tutorials, have said, can't one use polar coordinates to solve these problems? And in fact, you can. You still need to phrase it as a squeeze theorem, but sometimes it can be easier to use polar coordinates. So what I'm going to do is I'm going to kind of re-demonstrate exercise 70 doing polar coordinates, and in the handbook, I have phrased that as exercise 75. But 75 is really a revisit of 70, just using a different method. Polar coordinates can make the job easier. How do they make it easier? They take away that sort of design element. Okay, I've taken the example away now. But if you use polar coordinates, you no longer have to design a thing on the right that fits the three requirements. But the slippery thing with polar coordinates is that in the case of limits that don't exist, you can sometimes use polar coordinates, and if you're not careful, if you're not paying proper attention to what you're doing, you can think that you prove that the limit does exist when actually it doesn't. So polar coordinates are a little bit slippery that way. You've got to really keep an eye on them, or you can think they're telling you one thing when they're actually telling you something different. Okay, so polar coordinates can make the job easier. Be careful because using polar coordinates in situations where the limit does not exist, please keep quiet, can appear if you I just want to say, if you don't think carefully enough, that if you can appear if you, what's the wording I want to use here? Let's say if you are careless. Can appear if you are careless to say the limit does exist. Okay, all right. So how would I do? So 75 is a revisit of 70. We want to check out the limit of 3x squared y over x squared plus y squared as xy tends to 0, 0. Okay. So we still set it up as a distance. Okay, let me actually put in, okay, there's nothing wrong with what I've just written, but there's an extra line I want to put in between. So let's write here, consider the distance okay, we're going to set it up as a squeeze theorem again. Come on, stylus, catch up with me, please. Woo! 3x squared y over x squared plus y squared minus 0. We know it's got to be bigger than 0 simply because it's an absolute value. This is equal to, so what I'm going to do is I'm going to replace all the x's with r cos theta, and I'm going to replace all the y's with r sine theta. So it's going to be 3r cubed cos squared theta sine theta over x squared plus y squared. You can write r squared cos squared theta plus r squared sine squared theta, but you may as well just recognize that that's r squared at the bottom there. Okay, cancelling the r's is unproblematic. What have we got there? We've got 3r cos squared theta sine theta. Okay. Now here is where, in our problem it would be fine, but in other problems it wouldn't. It's very tempting to just say, okay, if x and y are tending to 0, then r is tending to 0. So let's just make r tend to 0, and clearly that thing on the right is going to tend to 0. And you'd be correct. But you'd only be correct because the cos and the sine are not interfering with that process. And sometimes the cos and the sine can interfere with that process in a different example where the limit does not exist. So I'm just referring back to these things can be slippery. Yes? Well, in this one they can't. But if, for instance, you had a divide by cos theta, then you might think, oh, well, because the r's in the numerator, r's tending to 0, everything's fine. But cos could be 0 for certain thetas, and yeah, that sort of thing. Yes? Question in the front? How did I get r cubed? Because it was, the x is r cos theta, so the x squared will be contributing an r squared, and the y is r sine theta, so the y is contributing another r. Glad you asked that question. I'm sure lots of people were wondering. Okay, I just want to write this carefully. This is now, so let's have a look. Sine theta, we know lies between, let me chop this up. I just want to be absolutely explicit about what's going on here. We know that the modulus of sine theta can only be between 0 and 1, and the modulus of cos squared theta can only be between 0 and 1. So, question? Okay, so we know that the thing that we're really interested in, that distance expression, we know that it's greater than 0 because this is an absolute value, so immediately I have an inequality. However, up until this last line, everything I've said is equal. There's been no, the thing on the right has been equal to the, or at least I shouldn't say the thing on the right. Every expression has been equal to the preceding one. So that thing with the x's and y's is equal to that thing with the r's and the cos's, which is equal to the line below, which is equal to the line below, but only on this bottom line have I replaced the cos theta and the sine theta with their maximum amount, and hence introduced an inequality. So I don't know whether that answered your question. I can't remember. Who was it who asked it? Somewhere below. So you only put the inequality sign when in fact you have two things that are unequal, and that only happened in this very last line. Now we can talk about r tending to 0. Xy tends to 0, 0 is equivalent to r tends to 0 from above. You could just say r tends to 0, it's fine. So the limit of 3r as r tends to 0 from above is equal to 0. The limit is xy tends to 0, 0. Or you could say r tends to 0, 0. Therefore, by the squeeze theorem, sorry, I can hear someone's trying to talk to me, but I just want to finish writing what I've written. Have I made a mistake? Just want to finish this. Right, there, I can hear there was a question. Yes, over here.
Second last line. What happened when the second last line is the last line?
Okay, so I know that cos squared theta lies between 0 and 1, and I know that sine theta lies between 0 and 1. Therefore, I know the biggest cos squared could possibly be as 1, and the biggest that sine can possibly be as 1, and hence the biggest that product of those three factors could possibly be as 3r. So by replacing that product of three things with 3r, I've replaced it with its absolute possible maximum, and hence that's why the inequality came in. I know 3r is as big as that product can possibly be. In fact, logically speaking, it'll never be as big as 3r, because cos squared theta is never equal to 1 for the same theta that sine theta is equal to 1. However, that doesn't, so you could even, if you wanted, drop the equality on that very last thing. But that's for our purposes, we're just replacing each factor with the largest it can possibly be. But there was a question over here before you, yes? You had something else, this side, yeah? Yeah, but it's modular. We're talking about that side teaching here. So we're talking about repeat on so what side teaching here? Okay, cool. Now we're asking another other question over there.
Saying that the theta variable cannot produce the different, like cannot produce the same value for sine and cos.
We're certainly not one, yes.
Yeah, so how is it that the multiplication of both cos and sine is 1?
Well, I'm not saying that their product is 1. I'm saying that it's the maximum that it could possibly be. That's why I've got an inequality, not an equality. I'm not saying cos squared times sine theta equals 1. I'm saying cos squared theta times modulus of cos squared theta times the modulus of sine theta will always be smaller than 1.
So we're assuming you put different values for theta.
Well, it has to be. Whatever you say, that has to be true for all theta. I'll come back to that, but let me take this question.
Ma'am, when we're talking about x and y, we're not limiting it to any positive, negative, anything like that.
Correct.
Then theta will also not limit to anything between 0 and 2 pi, right?
Correct. So theta can be anything between 0 and 2 pi. Yes, absolutely. So what we've kind of done here, there's kind of an invisible 1 here. There's kind of an invisible 1 here. The maximum that mod cos squared theta, mod sine theta can be. And as I said, actually, we could even drop the equality because strictly speaking, they'll never actually be as big as 1, but that's fine. That's fine. What we're wanting to do is we're wanting to simplify that right-hand side of our inequality into something that we know for sure is going to tend to 0 as r tends to 0. Question over here?
Actually, the limit tends to r, limit as r tends to 0 from the right. From the right, because r is the maximum.
Because r is always positive. So the reason why I've said r tends to 0 from above is because r is always positive. R is a positive measure from the origin. But really, I'm not too sticky about that. If you want to drop the plus, you can, because there are quite bizarre cases where one actually does accept the existence of negative r's when you're dealing with funny parametric curves and things. So I'm not a stickler about that in this context. There's other contexts where I am. Question?
How can we drop the inequality over there if we're saying that it's going between 0 and 0 but not equal to either?
Because it's a limit. So the limit of 0 is clearly 0. The limit of this 3r is 0. And so then the limit of the thing in the middle is 0. Even if they're never actually equal to 0, their limit is 0. Does that help?
Yeah.
Sort of, except limits never help. Limits just bend your brain. Question over there. Okay, let me scroll up one line there. I replaced the x with r cos theta, and I replaced the y with r sine theta. So that's all I did in that sort of top thing on the right. And then after that, I cancelled the r squared, which is fine. I can do that. I know that because remember, I'm going to make r tend to 0. R is never going to be equal to 0. It's going to tend to 0. So division by r squared is fine, not a problem. And then I just basically sit and look at what's there, 3r cos squared theta, and think, what can I do with this? And what I can do with it is I can say, I know cos squared is always going to be smaller or equal to 1. I know sine theta is always going to be smaller or equal to 1. So therefore, if I simply replace them both with 1, I introduce that much needed inequality sign. I need that inequality sign in order to have a squeeze theorem. So equal signs are fine and dandy, but they're no use for squeeze theorem. Squeeze theorem needs inequalities. Okay, you're always free to use polar coordinates in these problems. They can make the problem easier, but as I say, they're slippery. They're slippery, and sometimes you can think that something's the case with a little bit of deep thought. You realize, oh, actually, maybe it's not. So I'm happy for you to use polars or not. I know some lecturers are happier with polar coordinates than others. In mainstream, I know Abraham Fredericks is fine with polars, but I know, or at least historically in previous years, Neil Robertson he's not happy with people using polars because he knows how easy it is to make mistakes with it. So I don't know whether your friends in mainstream are doing polars or not, actually. Question over there?
Why would you say that x and y on the side?
Because x and y tending to 0 is equivalent, because if you've got your points tending to 0, if you're approaching 0 as far as x and y are concerned, then you're also approaching 0 as far as r is concerned, because r is a measure of distance from the origin. R is basically defined as distance from the origin. So here's an interesting point. What if x, y we're not tending to 0, 0, but we're actually tending to 1, 2? What if your point was actually 1, 2? Then if you were doing things in rectangular coordinates, it wouldn't matter. It really wouldn't matter. If you were, the tending to 1, 2 is something you would just take in your stride. But if you wanted to change to polar coordinates, you'd be in a bit of a mess. Because tending to 1, 2 is completely different from r tending to 0. R tending to 0 means your point has to be the origin. So there's an important point. You could only use polar coordinates if the point that xy is tending to, in fact, is the origin. If the point that xy is tending to is not the origin, polars are no use to you. You'd have to completely reconceptualize your problem to be able to use polars. So there you go. There's another slippery thing about polars. So thank you for making me think of that. Okay, I'm going to rub this out because it's not... I'll just leave that in. Anybody just looking at the PDF would be confused if I left that in. All right, we need to move on. Let's talk about partial derivatives. Yay, calculus. Let me change color. Come on, let me change color. What are we going to do? I'll go for dark blue. Okay. Please keep quiet. Please keep quiet. Come on, guys. Please keep quiet. Oi, come on. It's not hard. Shush. A function of several variables can be differentiated with respect to one variable at a time. I'm realizing that by taking my table away, they've taken away our coordinate system for the class. We're floating in some sort of coordinateless limbo. Somebody must have tried quite hard to remove that table. It was quite a heavy table and it's gone. A function of several variables can be differentiated because now we're wanting to use a coordinate system and I don't have one. With respect to one variable at a time, holding all other variables constant. Okay, somebody's leaving a note on the Padlet. That's very exciting, right in the middle of class. Woo! You might not be excited, I'm excited. And here is some notation. Okay, so before, notation-wise, if you had f of x equals x squared and you wanted to differentiate that, you would write f dash of x. We still do use dashes in certain contexts, but for partial derivatives we cannot. Because if our function is a function of x and y, and we use a dash to signify differentiation, which variable are we talking about? So instead we use a different notation. We use a little subscript, and we say f sub x. That means the derivative with respect to x. We could also use the d by dx notation, but then notice it's a curly d. Okay, it's a curly d, not an ordinary d. Alright, so anybody looking at df by dx, they would know, even though you haven't said so, that f is a multivariable function. Otherwise you wouldn't be using partial differential notation. Yes?
Is that like between f prime and xy, or is it just...
There's no prime. There's no prime. It's just a little subscript x. And the sort of first principles formula is very similar to the one you already know. But notice what's happening here. X is the thing that's varying in the numerator, y is not. X is being allowed to vary, y is not. Let me write down the equivalent y. Oh, I see, it's my handwriting. My F's have a sort of a curl at the top. Yes, there's not a dash. I have such terrible handwriting. Okay, you can use H again, but I prefer to use K. Okay, so what's happening there? There, y is being allowed to vary, but x is not. Okay, so coordinate system. It was somewhere over here, the coordinate system that I missed. Okay, I'm standing at the origin or not, so I'm standing at some point in space. Okay, x-axis is directly, is parallel this way. Oh, come on, I need a right angle. Okay, the lectern has a right angle. There we go. All right, so here's my x-axis, and here's my y-axis, and here's my z-axis, and there's my origin. Okay, so imagine you're standing at some point in space. Your x derivative would be, let's have a look, x is varying, and this is our x-axis. Okay, so I'm standing at a certain point. I have an x coordinate, I have a y coordinate where my feet are. In order to envision what your x derivative is telling you, it's the slope. Let me stand further back so that the mic can pick me up better. It's the slope if you walked in the direction of increasing x but kept your y coordinate constant. So I'm going to walk parallel to the parallel to the x-axis, orthogonal to the y-axis. So if I walk like this, let's say I'm walking uphill, then my x derivative will be positive. If I'm walking on the flat, my x derivative will be 0. If I'm walking downhill, my x derivative would be negative. My y derivative would be the exact opposite. I would now face with my back to the x-axis. Well, and I'd be facing, I want to go walk parallel to the y-axis in the direction of increasing y, and orthogonal to the x-axis. So then I walk over once again, if I'm walking uphill, y derivative is positive, on the flat 0, downhill. Now, of course, those two things might be completely different. Imagine standing on the side of a mountain. This direction might be really steep uphill, but this direction actually be slightly, less steep downhill. So your two derivatives could be completely different to one another. If you happen to be standing on a contour path on the side of a mountain, then maybe if you turned this way, your slope would be 0 because you wouldn't be going up or down. But this way, maybe it's very steep up to the top of the mountain, or in fact, maybe very steep down to the bottom of the mountain. So your two derivatives really don't have to have anything in common.
Sorry.
Yes?
On the first line after the parallel, you see that the function is equal to the derivative.
What I'm given here is two different notations for the derivative. Two different derivative notations. So that thing on the far left is not the function, it is the derivative. And the little subscript is what's denoting that. I don't know whether I'm addressing your concern. So it looks an awful lot like the function notation, but it's just got that little subscript, and that little subscript means derivative. So it's just like a dash, but the dash is just insufficiently informative when our function is a function of more than one variable, so we have to turn to slightly different notation. Question? There was a hand up? Yeah? Okay, I beg your pardon, I can't hear you. A drawing, oh my goodness, you want me to do a 3D drawing. Ah, yes, surely I'm up to this task. Let me do it. Here we go. Ah, no, don't jump page. Let's have a look. Okay, let me demonstrate. Let me draw with a paraboloid. Here's a paraboloid. There's my z-axis. Okay, all right. Let's say I'm standing at a point. I'm standing over there on the paraboloid. There's a little ant standing over there on the paraboloid. Please keep quiet. If you could please keep quiet. Okay. If that little ant decided to walk in the direction of increasing x, it would be walking there. If it decided to walk in the direction of increasing y, it would be walking maybe there. Okay? Parallel to y-axis, downward slope. This one will also be downward, but depending on the dimensions of the paraboloid might not be, and exactly where you're standing might not be quite the same slope. Parallel to x-axis. Yeah, no, this is just a rough diagram, but the way I've drawn my arrows, downward slope, let's say, for example, fx at AB equals, say, -1/2. But maybe here, fy at AB equals, say, -2, or something like that. So the little ant that's standing over there, if it moves in the x direction or the y direction in my picture, it'll be moving downhill. But in my little example here, if it moves in the x direction, it'll be slightly less steep downhill. If it moved in the y direction, it would be quite steep downhill. Question?
You're talking about the positive and negative derivatives. You're talking about the change in z-values.
Yes. Yes. So this is basically your change. This is how so the derivative is kind of saying, here is how z changes if you change x, or here is how z changes if you change y. And whether you're changing x or whether you're changing y can leave you with quite different answers to the question, to the calculation of slope. Okay, what do I want to say? Oh, right, yes. Once again, just like with limits, stepping up in one dimension actually makes a big difference in the number of tangents. a curve in R2 has only one possible slope and hence one tangent line. Catch up with me, stylus. Woo, that's cute. Let's rub that out. What was I saying there? And hence one tangent line at a point. Okay? A surface in R3 has infinitely many slopes, possible slopes. And in fact, you could add an adjective there and say direction-dependent slopes. Okay, if you've been in my class before, you know I cannot spell dependent. I cannot spell dependent or independent. I never know whether it's dent or dant. Ever. There's a hole in my brain where that word goes. It could be, count my blessings. That seems to be the only real hole in my brain, but I cannot spell dependent, so please don't hold it against me. Slopes and hence infinitely many tangent lines. At a point. Because after all, if I'm standing at that point on the mountain, yes, I could move in the direction of increasing x. Yes, I could move in the direction of increasing y, but I could also move anywhere in between, maybe at 45 degrees or 30 degrees, or how about over there? Or how about in this direction? There's infinitely many directions that I can walk when I'm standing on the side of a surface, when I'm standing on a surface, and hence there are infinitely many slopes. We're going to be doing something called directional derivatives, and directional derivatives will be those slopes, those direction-dependent slopes. Your x derivative and your y derivative are simply two special cases of direction-dependent slopes. Yeah, so for a curve in, well, let's have a look. Let's say you have good old-fashioned curve like that, like you had back in first year. At any one point, there's only one slope, there's only one tangent line. In 3D, if you have some sort of space curve, at one point, there is still only one slope and only one tangent line. Derivatives, your formal derivatives always assume direction of increasing x, direction of increasing y, so hence only one. But then, just to reiterate what I've been talking about, at a point here, there's, you can draw a star. There's infinitely many tangent lines that pass through that point. Okay, let's have a look. We have 5 minutes left. What else do I want to say about partial derivatives? Okay, so your x derivative is the slope of the tangent line parallel to the xz plane, and fy is the slope of the tangent line parallel to the yz plane. Okay, all right. Is there anything else I want to say before jumping into an example? Explain formula. Right, okay, I'm just looking at my notes. Let me jump into an example and do exercise 76. All right, differentiate from first principles, it says, to find the partial derivatives of f of xy equals x over y. Okay, now, on the one hand, we're not going to ask you a question like that in tests and exams. However, we are going to ask you questions to do with differentiability, where you are going to have to differentiate things from first principles, and I will draw your attention to the questions on page 31 and 32. 31 and 32, those exercises, you're going to be doing a lot of first principles differentiation. So let's just reintroduce ourselves to the concept with something slightly less exciting than those questions. 76. Right, there we go. So the x derivative, limit as h tends to 0. Please keep quiet. Okay, you remember how to do these things. Limit as h tends to 0 of, actually, that's very poor technique for me to do it alongside. Let's do it here. Let's have a look. Let's collect that together into one fraction. So that would be so that's just going to be 1 over y, which is what you'd expect. So basically all of your rules of differentiation still apply. All of your rules of differentiation still apply, but you just have to keep in mind which variable you're differentiating with respect to and which variable you're holding constant. Okay? So if we're differentiating with respect to x is the variable and y is playing the role of a constant. So x over constant, if you differentiate it with respect to x, will just leave 1 over that constant. Okay, so what would you expect? Just using your differentiation rules, what would you expect the derivative with respect to y to look like? And does first principles give us that answer? Let's have a look. What is it? It would be x over y plus k minus x over y all over k. I'm going to smoosh those two fractions together into one fraction. So that's xy minus x times y plus k. And there's a k at the bottom as well. So let's have a look. I'm going to have xy minus xk. Catch up with me, stylus. Thank you. Minus xk. And at the bottom we've got y plus k. We can cancel the k's. And if we allow k to tend to 0, we have minus x over y squared, which is exactly what you would expect if you took that x over y, pretended x was a constant, and differentiated with respect to y. Because 1 over y differentiates to minus 1 over y squared. Okay, so not only is this a little bit of practice on differentiating from first principles, but it's confirmation, or at least confirmation is too strong a word. It's comforting to see that our differentiation rules seem to still apply, and in fact they all still do. Okay, according to my clock that's the end of the period. What I would like to do is ask you to do exercise 77, but rather than wasting time on, it's Friday, isn't it? Rather than wasting time on Monday morning's lecture doing that, I'm just going to leave that as homework, number 77. But why don't you just give it some practice? You are going to be differentiating from first principles, so don't try and pretend it doesn't exist.